All right, so all that's left for us to do on the topic of subspaces is to cover a couple of theorems. So the first theorem concerns what happens if you have several subspaces of a specific vector space V, and if you take the intersection of all of those. So let's read this theorem. Suppose W1 through WR are subspaces of a vector space V. Then the intersection of all of those subspaces is guaranteed to be a subspace of V as well. Now remember, back in our preliminary section, we talked about what this operation means. The intersection of two sets is a set containing everything that these two sets have in common. That definition extends to an intersection of any number of sets. So when we talk about this, W1 intersect W2 all the way to WR, we're talking about a set that contains everything that that all of these subspaces have in common. Okay, now the proof that I wrote here is actually leaving out kind of an important step. So I do want to write something in here to make sure that what we do is valid. Remember, a set can only be a subspace of a vector space if that set is non-empty. And by the assumption here that W1 through WR, by assuming all of these are subspaces, that would imply that they're all non-empty. But what guarantee do we have that their intersection is non-empty? Remember, in order for this intersection to be non-empty, then there has to be at least one vector that every single one of these has in common. But because these are all subspaces, that would make them vector spaces, and every single one of them needs to contain the zero vector from V. So they have at least the zero vector in common. Let's write that in. Since W1, W2 through WR are subspaces of V, each one contains the zero vector. Thus, the zero vector is in the intersection so that intersection is non-empty. Okay? Got a little bit sloppy there, but I forgot that important detail when I wrote this proof up. We need that there. And the reason we need that is because that allows us to do the next step. Notice I say let U and V be vectors in this intersection of subspaces. I wouldn't even be allowed to say this if I didn't already know something lived in that set. But now we've established that at the very least, U and V can both be the zero vector. But they could be other things too if there are more vectors in common. So now, moving on with this, let U and V be in this intersection and let K be a scalar. Remember, if we want to show that this is a subspace of V, then we need to show that we have both closure properties, closure under both operations. That's our subspace test. I'm just going to show closure under scalar addition, vector addition, because closure under scalar multiplication will follow similar steps, and it's a good exercise to see if you can prove that on your own. So let's let these two vectors be in this subspace. K is going to be a scalar, and I'm actually not going to use that scalar K because that would be used down here. Because U and V are in this intersection of all of these sets, that implies that both of these vectors belong to every single one of these vector spaces, W1, W2, WR, and so on, which I'm stating here. U and V belong to WI, where I is equal to 1, 2, 3, 4, all the way up through R. That's because the intersection contains everything that these have in common. So if that's the case, for each one of these subsets, each WI is a subspace. So in each one of these is closed under addition. That means U plus V will also belong to every WI, each one of those subspaces. However, if it's in all of them, then that means U plus V would also belong to the intersection of those subspaces because it's a common vector in all of those subspaces. So that establishes closure under addition. The fact that u and v are both in this intersection was enough to prove that their sum belonged to the intersection as well. And again, we're going to skip the part where we prove closure under scalar multiplication. It's very similar. Okay. Last up for this section, an important theorem that takes us back to systems of linear equations. So in this one, the solution set of the homogeneous linear system AX equals 0, where this linear system has m equations and n unknowns. Remember, that corresponds to the rows of A, and this would correspond to the columns of A. That would mean A is an m by n matrix. Okay. If this linear system is defined this way, then the solution set of that homogeneous linear system will be a subspace of Rn. Remember, if this is an m by n matrix, then the column vector x has to have n rows. So this is an n by 1 vector, which we think of as a vector in Rn. All right, let's prove this. This proof was taken straight from the book. It's very straightforward. Let's let W be the solution set for our system. Remember, if we want to use our subspace test to show that our solution set is a subspace of Rn, I first need to show that it's non-empty. That is, I need to show that there's at least one solution to this linear system. But we know that for a homogeneous linear system, the trivial solution is always a solution. So homogeneous linear systems will always have at least x equals 0 in their solution set. That establishes that not only does the solution set have something in it, but it also has the 0 vector specifically. Now that we've shown that it's non-empty, we can verify our closure axioms. So first of all, let's suppose that x1 and x2 are both vectors in this set W. That would mean that each one of these is a solution to our homogeneous linear system. Or said equivalently, ax1 would equal 0 and ax2 would also equal 0. What am I trying to do with these vectors? I want to show that if I add them together, that the sum is still in our set W. But that's the same thing as saying that the sum of these vectors is another solution to our homogeneous linear system, which we can verify by plugging x1 plus x2 into this equation and checking. So a times x1 plus x2, because of our distributive property, is ax1 plus ax2. But because each of these is equal to 0 by assumption, this is equal to 0 plus 0, which is 0. That means x1 plus x2 is a solution to our homogeneous linear system, which puts it in W. Therefore, W is closed under addition. Scalar multiplication is similar. If I multiply any solution, let's say x1, by a scalar k, where k can be any scalar, by our homogeneity property, I can take the k out and do k times ax1. But ax1, we know, is equal to 0 because x1 is a solution to that system. And k times the 0 vector, regardless of what k is, will always be the 0 vector. We've proven that that would be the case. So we also have closure under scalar multiplication. Okay? What that tells us is that the solution set of a homogeneous system in n unknowns is always a subspace of Rn, and because it's always a subspace, we now are going to refer to solution sets for homogeneous linear systems as solution spaces. Okay, now a little bit on solution spaces. Let's focus specifically on a 3x3 system, a system of equations in 3 unknowns and 3 variables. The solution space for a homogeneous linear system with 3 equations and 3 unknowns should be a subspace of R3, because that's where the solutions will live. Here, we showed what a couple of subspaces of R3 look like. They look like either lines through the plane, or sorry, lines through the origin, or planes through the origin. It turns out that every subspace of R3, with 2 exceptions that I'm going to talk about, every subspace of R3 is always going to be one of these 2 types, either a line through the origin or a plane through the origin. The other 2 types are the trivial subspace or the 0 subspace. Remember, the set containing only the 0 vector is, by definition, or not by definition, but by what we showed back in 4.1, it's a vector space, so that makes it a subspace of R3 as well. And R3 itself is considered a subspace of itself. Remember back in our preliminary section, every set is a subset of itself. So every vector space would also be a subspace of itself. But those two are kind of the boring cases, either a single point or all of R3. There's not much interesting going on there. Aside from those, every subspace of R3 is either a line or a plane. So what that means is that every solution space to a homogeneous linear system with 3 equations and 3 unknowns will look like a line or a plane through the origin when we think of those solutions as vectors that we graph. Okay, that's going to be it for 4.2.